Imagine a traditional orbital launch vehicle. It is not merely a machine. It is a flying labyrinth comprising over 100,000 highly specialized discrete components. Now, erase that paradigm. Welcome to the $8 billion revolution of aerospace engineering, the fully autonomous monolithic 3D printed rocket factory. Here, the traditional 24-month assembly cycle is annihilated, reduced to a mere 60 days. The component count plummets from 100,000 down to less than 1,000. This is not science fiction. This is the brutal, hyper-efficient reality of next-generation additive manufacturing, where raw aluminum alloy is transformed into a towering, deep space-capable orbital vehicle entirely under the control of artificial intelligence and robotic precision. To comprehend the magnitude of this engineering leap, we must first dissect the fundamental physical limits of traditional aerospace manufacturing. For decades, the construction of a rocket fuselage has relied on a fragmented, globally dispersed supply chain. Fuselage barrels, propellant tanks, and engine mounts are forged in separate facilities, transported across continents, and integrated using thousands of mechanical fasteners, rivets, and multi-material welds. Each of these junctions represents a critical vulnerability, a point of potential mechanical failure. When a launch vehicle accelerates through the lower atmosphere, overcoming maximum dynamic pressure, or max Q, the airframe is subjected to unimaginable acoustic vibration and aerodynamic stress. At a microscopic level, every rivet hole is a stress concentration point. Every dissimilar metal weld is a battleground of mismatched thermal expansion coefficients. A microscopic fracture or a tolerance deviation of just 1/1000th of an inch at these junctions can lead to catastrophic pressure loss and structural disintegration. The monolithic 3D printing approach systematically eliminates these failure vectors by eradicating the joints themselves. By utilizing large-scale metal additive manufacturing, the rocket is no longer an assembly of parts. It is a single, continuous, homogeneous structure. There are no secondary bulkheads, no overlapping structural frames, and no thousands of drilling points. This structural uniformity is achieved through advanced topology optimization. Sophisticated algorithms calculate the exact load paths and stress distributions that the rocket will experience during ascent. Consequently, the printing robots can deposit thicker layers of material strictly where structural reinforcement is required and thin out the walls in low-stress zones to shed unnecessary mass. The result is an airframe that possesses an unprecedented thrust-to-weight ratio, maximizing payload capacity while maintaining absolute structural integrity under extreme dynamic loads. The physical limit of aerospace engineering is no longer dictated by how well we can bolt pieces together, but by how precisely we can control the metallurgical properties of a continuous weld. Stepping onto the floor of a giga-scale rocket printing facility is akin to entering the central nervous system of a hyper-advanced industrial organism. The space is vast, spanning hundreds of thousands of square feet, yet entirely devoid of the chaotic clamor associated with traditional heavy manufacturing. Instead, the environment is dominated by the low rhythmic hum of high-voltage transformers and the blinding, rhythmic flashes of plasma arcs. Standing at the center of this facility are the robotic print self-stowering, multi-axis robotic arms mounted on linear tracks or enormous gantry systems. These are not standard industrial robots. They are custom-engineered leviathans standing over 30 feet tall, possessing the payload capacity to wield heavy deposition heads while maintaining spatial positioning tolerances measured in single-digit micrometers. These mechanical arms move in a mesmerizing synchronized ballet, guided by millions of lines of G-code generated directly from the rocket's digital twin. As the robotic arm orbits the growing rocket chassis, it extrudes a proprietary high-strength aluminum alloy, layer upon microscopic layer, continuously building the fuselage from the base plate upwards. The scale is staggering. A primary propellant tank capable of holding thousands of gallons of cryogenic liquid oxygen is materialized out of thin air in a matter of days. This is the dawn of the software-defined factory, where the transition from a digital CAD file to a physical orbital class structure is seamless, automated, and relentlessly precise. Let us examine the specific metallurgical challenges overcome in this monolithic construction. Traditional aerospace aluminum such as the 6000 or 7000 series is notoriously difficult to 3D print. When subjected to the rapid heating and cooling cycles inherent in additive manufacturing, these alloys are prone to hot tearing and severe micro-cracking. To solve this, metallurgists had to engineer entirely new, proprietary alloy soften utilizing scandium or zirconium as alloying elements. These custom alloys are designed specifically to manipulate the solidification dynamics. When the plasma arc melts the feed wire at temperatures exceeding 3000 degrees Fahrenheit, the molten pool must solidify almost instantaneously to hold its shape, yet maintain a crystalline structure that prevents microscopic fissures as the print head travels at speeds of several inches per second, depositing up to 20 pounds of metal per hour, a localized shroud of inert shielding gas typically. A precise mixture of argon and helium is continuously pumped over the melt pool. This invisible atmospheric shield is critical. It displaces ambient oxygen and moisture, preventing the molten aluminum from instantly oxidizing and degrading the structural integrity of the fuselage. If this gas flow is interrupted for even a fraction of a second, the entire multi-million-dollar print must be scrapped. The margin for error is absolute zero. Let us delve deeper into the mechanical heart of this $8 billion operation. The primary additive manufacturing system, often spanning a footprint large enough to accommodate a commercial airliner hangar, utilizes directed energy deposition or DED technology. Unlike conventional stereolithography or powder bed fusion techniques, which are strictly physically restricted by the volumetric limits of a sealed build chamber, this system is radically unconstrained. Picture a custom gantry system massive enough to straddle a commercial train locomotive. The architecture relies on synchronized, multi-articulated robotic arms equipped with highly specialized deposition end effectors. These arms glide seamlessly along precision-machined linear stators, utilizing heavy-duty rack and pinion drives and magnetic encoders to achieve a spatial positioning repeatability of less than 0.05 mm. Dimensional tolerance thinner than a human hair, maintained across a mechanical wingspan of over 40 feet. The raw material, consisting of continuous spools of aerospace-grade aluminum wire, miles in length, is relentlessly fed through a motorized wire guide mechanism directly into the deposition head. Here, a high-intensity plasma arc, or in some specific configurations, a multi-kilowatt solid-state laser array, instantly liquefies the metal wire. The deposition rate is a relentless metric, achieving an output of up to 1,000 kilograms of structural mass per week per print cell. However, melting metal at an industrial scale is merely the operational baseline. The true engineering marvel lies in controlling how that metal solidifies. This brings us to the most formidable technical barrier in macro scale, metal 3D printing, the management of thermodynamic deformation and residual stress. When constructing a monolithic propellant tank that stands over 100 feet tall, the physical laws of thermal expansion and contraction become an existential threat to the structural viability of the vehicle. To understand the scale of this thermal challenge, consider that the printing system is actively injecting megawatts of concentrated thermal energy into the aluminum structure over a continuous period of weeks. As the plasma arc deposits a new layer of molten aluminum at temperatures exceeding 1,600 degrees Fahrenheit, the underlying layers of the fuselage are simultaneously radiating heat into the ambient environment and rapidly contracting. This extreme and localized thermal gradient generates massive internal shear forces within the crystalline structure of the alloy. If left unmanaged, these localized physical stresses accumulate exponentially layer by layer. The inevitable result is catastrophic geometric warping, where a perfectly cylindrical booster section curls inward, deviating from its optimal aerodynamic profile by several inches. Worse, the internal tension can easily exceed the baseline yield strength of the material, causing the thick metal structure to spontaneously fracture and rip itself apart on the manufacturing floor before it ever interfaces with a launch pad. To conquer this severe physical limitation, the printing process cannot be a blind, open-loop operation. It demands an unprecedented level of real-time, closed-loop sensor integration and computational oversight. Surrounding the plasma deposition head is a complex array of non-destructive diagnostic instruments operating in parallel. High-speed infrared thermal imaging cameras monitor the melt pool geometry and the exact cooling rate of the immediate heat-affected zone at over 10,000 frames per second. Simultaneously, optical interferometry sensors and laser scanners continuously map the macroscopic dimensional accuracy of the growing cylindrical structure. This torrent of sensor data totaling gigabytes per minute is fed via fiber optics into a central computational cluster. Here, proprietary machine learning algorithms analyze the thermal dynamics of the metal on the fly. If the system detects that a specific quadrant of the fuselage is cooling too rapidly, risking severe contraction, the software instantly intervenes without human input. It dynamically modulates the electrical current of the plasma arc, adjusts the wire feed speed, or alters the robotic travel velocity to inject more or less thermal energy into the precise coordinate location. Furthermore, the central software dictates the overarching deposition strategy known in the industry as the toolpath generation. To prevent thermal energy from critically concentrating in a single hemisphere of the rocket body, the printing algorithms calculate highly complex, non-linear deposition patterns. The robotic arms may print a thick structural segment on one side, then rapidly index to the exact opposite side to balance the thermal load, effectively weaving the metallic structure in a calculated algorithmic thermodynamic sequence. Every single voxel of the aluminum airframe is logged, analyzed, and certified in real time as it transitions from a liquid plasma to a solid state. This digital twin holds the complete metallurgical history of the rocket, drastically reducing the need for extensive post-fabrication inspections that traditionally bottleneck aerospace manufacturing. Once the primary additive phase concludes, the monolithic structure is not yet ready for orbital flight. While the 3D printing process achieves near-net shape geometry, the critical interface points such as the mating rings for the orbital payload fairing or the reinforced thrust puck, where the main engines attach require absolute mathematically perfect flatness to ensure pressure seals. Therefore, the same facility houses enormous vertical turning lathes and multi-axis CNC milling centers. The entire printed stage, standing as tall as a 10-story building and weighing several tons, is horizontally transferred via autonomous guided vehicles into the subtractive machining cell. Here, carbide cutting tools rotating at thousands of revolutions per minute shave away microscopic layers of the rough printed aluminum, achieving surface finishes measured in fractions of a micron. This hybrid manufacturing approach, additive for the primary mass, subtractive for the critical mating interfaces, represents the absolute apex of current industrial capabilities. Before the monolithic structure can be integrated with its propulsion systems, it must undergo a rigorous suite of non-destructive testing, or NDT. The sheer volume of deposited metal presents a unique inspection challenge. Traditional X-ray methods are insufficient for analyzing a continuous variable thickness aluminum wall that spans over 100 feet in length. Instead, the facility employs automated phased array ultrasonic testing crawlers. These robotic units adhere magnetically or via suction to the curvature of the fuselage, traversing the entire printed surface. They emit high-frequency acoustic waves into the metallic matrix, analyzing the back reflection signatures to detect internal anomalies. The tolerance threshold is exceptionally strict. The system is calibrated to identify microporosities or lack of fusion defects with a diameter smaller than 0.1 millimeters. Any volumetric void exceeding this microscopic parameter could propagate into a critical fracture under launch conditions, rendering the stage non-compliant for flight. For the thickest structural sections, such as the engine mounting thrust puck, industrial computed tomography, or CT scanning, utilizing linear accelerators generating mega-electron volt X-rays, provides a complete three-dimensional volumetric reconstruction of the internal grain structure. Following structural validation, the ultimate physical threshold is evaluated through extreme mechanical and thermodynamic stress testing. The most critical of these is the cryogenic proof and burst test. The fully printed propellant tank is transported to an isolated, heavily fortified testing bunker. Here, engineers pump thousands of gallons of liquid nitrogen, or in some iterations, subcooled liquid oxygen, chilling the aluminum alloy down to a sustained -196 degrees Celsius. This induces a severe cryogenic thermal shock, drastically altering the fracture toughness and ductility of the printed metal. Once thermal equilibrium is reached, high-capacity pumps force additional cryogenic fluid into the sealed tank, steadily increasing the internal hydrostatic pressure. The structure is first pressurized to its maximum expected operating pressure, followed by a proof pressure holding phase to verify seal integrity. However, for a qualification article, the pressurization continues relentlessly until the physical yield strength of the material is violently exceeded. The tank intentionally ruptures. High-speed cameras recording at tens of thousands of frames per second and thousands of strain gauges capture the exact millisecond of mechanical failure. This destructive data is paramount. It calibrates the topology optimization algorithms, proving exactly how the 3D printed alloy behaves at its absolute tensile limit under cryogenic conditions. The successful validation of these monolithic structures triggers a fundamental paradigm shift in the macroeconomic landscape of aerospace manufacturing. Historically, the production of an orbital launch vehicle relied on an incredibly fragile, globally distributed supply chain. Procuring specialized titanium forgings, custom-machined bulkheads, and thousands of aerospace-grade fasteners often involved dozens of vendors across multiple continents, resulting in a standard lead time of 24 months from order to assembly. The giga-scale 3D printing facility obliterates this logistical bottleneck by consolidating raw material intake to standard aluminum alloy wire and centralizing the entire manufacturing process beneath a single roof. The production cycle is compressed to just 60 days. This represents a 90+% reduction in manufacturing time. There is no longer a reliance on external suppliers for complex sub-assemblies. The factory operates as a closed-loop production ecosystem, where software iteration instantly translates to physical hardware. This is not merely a new method of building a rocket. It is the complete re-engineering of the aerospace industrial base, establishing a new baseline for rapid iteration, massive scalability, and the sustainable industrialization of low Earth orbit.